Hello everyone and welcome to week 9 about repeated games. I am David Smerdon. Before we get into it, let's have a little recap from last week. So what we'll start off with is the solution to a very cute little puzzle, little brain teaser you can bust out at dinner parties, the Lions and the Magic Lamb puzzle. Then a very quick review about Subgame perfect Nash equilibrium, what the concept means, why we care about it, and then we'll look at that in the context of repeated games. Now, repeated games is, I think, a very cool topic, more complicated than what we've seen so far, for sure, but I think that's what makes it so interesting, that it is quite rich, involves a little bit of mathematical trickery, but it's quite nice. But let's ease into things with our lions and the lamb puzzle. So this is a recap of that puzzle. We've got a group of hungry lions, a poor lamb sleeping in the field. The lions line up one by one, so we'll call the first lion in the line Lion 1, and then Lion 2, so forth. If the lion eats the lamb, the lion turns into a lamb. If the lion doesn't eat the lamb, it stays hungry. A lion prefers to eat the lamb and stay alive. It doesn't like to get eaten though, so if it's going to get eaten, if it becomes a lamb, it would rather just stay hungry. So the question is, what should the first lion do? And can our poor lamb survive even though it is surrounded by N hungry lions? What we are really asking for here is characterize the equilibria that emerge for different numbers of N. So to build up to that, one way to start is to start with very simple case, n is equal to 2, advance to n is equal to 3, try to spot a pattern and see if we can prove certain equilibrium results for n greater than 3. So let's start when it's just two lions, Lion 1 and Lion 2. And let's put Lion 1 in the shoes of Lion 2. So you're Lion 1. Think about what Lion 2 will do if you eat the lamb. Well, if you eat the lamb, you become the lamb. For Lion 2, there are no more lions around. The choice is to eat you with no repercussions or leave you alone. Probably Lion 2 is going to eat you. So you know this now. So what do? Do you eat the lamb? Well, no. If you eat the lamb, you'll be eaten. So you don't eat the lamb. And so what does Lion 2 do? Well, then Lion 2 is faced with exactly the same situation you were faced with before. And so we know what happens there. Lion 2's not going to eat the lamb. Nobody dares move towards the lamb. And our lamb lives. So exciting for the lamb. So with n equals 2, the lamb lives. So what happens if there are 3 lions? Well, again, you're Lion 1. You think to yourself, if I eat the lamb, what is Lion 2 going to do? Well, if you eat the lamb, you turn into the lamb. Now there are n is equal to 2 lions. We have exactly the same problem that we just solved. We have the n is equal to 2 problem, and we know what happens there. In equilibrium, the lamb lives. So knowing this, you should eat the lamb, because if you eat the lamb, you know what's going to happen. No lion will eat you. We already solved this. So knowing this, Lion 1 decides to eat the lamb. Let's just try n is equal to 4, but just particularly how we would solve this. So the way that we would solve this is Lion 1 thinks, if I eat the lamb, there are now 3 lions left. So n is equal to 3. We've already solved that. We know what happens. The first lion in that queue will eat the lamb. So if I eat the lamb in n is equal to 4, the next lion will eat me. So in that case, we know that Lion 1 does not eat the lamb. So what we're doing basically in each new number for n, we're rolling back the analysis. So for n is equal to 4, we're seeing how line 1 thinks about things as an n is equal to 3 problem. We're rolling back. So even though n can get very big, we've already solved all of the previous steps. And we've seen that sort of equilibrium analysis before. So in other words, for n is equal to 4, lion 2 will eat the lamb. So knowing this, lion 1 does not eat the lamb and the original lamb lives. And now we start to see a bit of a pattern. And the pattern is for even numbers of n, lion 1 does not eat the lamb because it would result in the lion being eaten. For odd numbers of n, lion 1 does eat the lamb. So we end up with a very strange scenario whereby even having 100 lions means that the lamb lives. What about subgame perfect Nash equilibrium? Well, it is difficult to understand what the purpose of this is compared to the regular Nash equilibria that we've seen before. Well, the key is to understand what a subgame is, what the different subgames are, and to understand that a subgame perfect Nash equilibrium is just a special category of Nash equilibrium. It's a refinement. It's a refinement such that in each subgame we still have a Nash equilibrium going on. So the subset of subgame perfect Nash equilibria must be smaller and contained within the total number of Nash equilibria. Sometimes they can be exactly the same, but it's always contained within the overall subset of Nash equilibria. So a simple example where there are only 2 Nash equilibria and only 1 subgame perfect Nash equilibrium is the father-son-girlfriend game that we saw before. Now we can write this game out in its normal form, and when we do so, we can solve for equilibria and find 2 pure strategy Nash equilibria from our 2x2 payoff matrix. They are end and disinherit and continue and accept. I'll move out of the way so you can see that. So we've found 2, but end and disinherit, as we spoke about before, seems a little bit strange as an equilibrium because of the fact that it involves this incredible threat. It involves the father threatening to do something that if we reach this point F, the father would not do, which is disinherit. We know the father would accept if he reached here. So it's an incredible threat. And in these extensive form games, the subgame perfect Nash equilibria give us those equilibria that don't involve these non-credible threats. And it can always be solved using backward induction. So what I used to do when learning this particular topic is to first transform your game tree into a payoff matrix, or in formal terms, transform the extensive form game into its normal form equivalent. From the payoff matrix, it's quite easy just underlining or putting stars to work out what all the Nash equilibria are of that game. Then going back to the tree, we can identify all the subgames that exist in our extensive form game tree. And we really want to know that what would have happened if something off the equilibrium path occurred. So for each of the Nash equilibrium strategies that we see, what happens if somebody deviates and we end up somewhere else along the game tree? What would have happened if? And there we want to see whether there are credible threats or not credible threats. And here, that's the real benefit of subgame perfect equilibrium as a concept. It basically says that there's going to be logical and rational play by both sides, even off the equilibrium path that actually occurs. A simple form of that is the centipede game, which we saw last time. So we'll take these 4 steps, when we write out this game in its normal form, we end up with a 4x4 matrix. And we can solve that in the usual manner to work out the set of Nash equilibria, of which there are 6. And all of these 6 actually involve the first player playing down on their first move. And when that happens, there's no incentive for player 2 to deviate from their chosen path, because in any case, player 1's going to play down, so player 2's decisions don't really matter. But on the other hand, for player 1, there's no incentive to change unless player 1 can do better than what he gets in equilibrium, which is 2. So unless player 1 can get 3, if player 1 can get 3, then it would actually be worth deviating. And when can that happen? Well, that can only happen if player 2 is going to play both A1 and A2. So when both A1 and A2 happens, then there's an incentive for player 1 to deviate. So that's why we don't have these outcomes as part of a Nash equilibria. We only have the 6 that are highlighted in blue. So at these 6, there's no incentive for any player to deviate, even though off the equilibrium path, some of these actions are a little bit stupid or irrational, we might say. And now we want to check the subgames one by one. And the easiest is just to start at the end and work our way back. So this is a subgame here, for example, right at the end. So we could start at this one at player 2's second decision node. And here, A2 is clearly dominated by D2. So we know that no Nash equilibrium that contains A2 can ever be a subgame perfect Nash equilibria. So that means that these guys in this column can't be subgame perfect Nash equilibria. And we can continue to do this for each of the 4 subgames that exist. The 4th is the entire game. So basically what we're doing is a form of backward induction, and then we find that there is only one Nash equilibrium that doesn't involve some irrational action off the equilibrium path, and that's when everybody chooses to go down whenever they get the chance at any decision node. Okay, let's move to today's topic. We are going to look at repeated games, but particularly using Prisoner's Dilemma as our main example. Now, we have already seen some examples of ways to use different mathematical tricks and tools to solve very long, or if you think about a game tree, very wide games, by rolling back in the same way that we essentially solved for the lions and lamb game for any n that could occur. For instance, in the Rubinstein bargaining game, there's sort of an infinite number of branches of x different proposals that can be put forward by a player, and we can get very large t different time periods. But what we can keep doing, for instance, in this case here, we can realize that if player 2 rejects the first proposal for a t period game, we've essentially now rolled back into a t-1 period game. In the same way as in if a lion eats a lamb in a t-lion game, we now have the situation of a t-1 lion game. So we're essentially using these tricks to roll back very long periods into shorter, more manageable periods. So let's revisit our favorite and famous game, the Prisoner's Dilemma. We know that there are many applications of this. The simplest is I do a favor for you, you do a favor for me. And that's how groups evolve and survive over time. But we know that the only equilibrium of this game is defect-defect, where the 2 players each receive 0, and so together we end up with the lowest aggregate payoff. And if this continued for some tribe, some community, as humans were evolving, this group would die out, because overall they're earning less in terms of payoff, which might be, say, collecting food or resources, than some other group that's always cooperating with each other. So through natural selection, there has been an evolution of personality traits and emotions that help to foster this cooperation type of instinct, such as feelings of matehood, helping each other out, solidarity, nationalism, empathy, altruism, and so forth, and the associated psychological rewards and punishments. You feel good when you help someone out, you feel guilty when you screw someone over. So these emotions have evolved because in any sort of prisoner's dilemma type environment, cooperation gives more payoff to those groups or individuals, which helps them to prosper and their offspring to survive, and so forth. Now, implicit in these sort of solutions is the fact that these games are not just played once, but played multiple times. So there are repeated interactions. So now we want to analyze this game in the context of a longer term play. And there are many examples, not just from evolution, but even today in different applications of the prisoner's dilemma. For example, trade and tariff wars between different countries, where obviously it's better for both countries if there are no barriers to trade, but there are incentives for one country to put barriers in place to screw the other over, but then there'll be retaliation and so forth. Any sort of cartel environment or collusion, such as OPEC deciding what prices to set for their oil or what quantities of production to put forward. Housemates deciding whether or not to do chores, such as when you cook, do you wash the dishes or leave it for someone else? And celebrity Hollywood couple partying all the time, deciding whether or not they should stay faithful to their partner or cheat on their partner. So these are all repeated type of interactions where there are essentially choices of whether to cooperate and do what's in the best interests of your partner and the best interest of you for the long term, or that short-term temptation to defect. So what we have with the repeated game then is essentially a gain tree, where at each node in the tree we have the same stage game, the same payoff matrix. So we play the same one-shot game at each point in a tree. For example, we play the game here at our first node, and if, for example, the outcome is CC, we then play if it's CC, we then play another game. So we get another payoff another payoff matrix, which is the same as before, and we play that game. If the outcome of the first game is CD, then we're moving down a different branch of the tree. So we've got a different history of play, a different past action has occurred, but we're still playing the same game in period 2. So we're essentially playing the same game, but branching off into different types of different branches in a tree depending on what's been played before. And as I mentioned, that's called a history. So that specifies the action profiles that have been played from the very start up until wherever we are now on the tree. And a strategy for a player in this case needs to assign an action in the stage game, in this case it would be cooperate or defect, to be played at each possible history that could occur. Now if you think about, say, playing 5 different rounds of this, then that can get very complicated, because round 1 different things could have happened, and then in round 2 different things can happen, round 3, and if you keep multiplying these permutations you end up with a huge number of histories. So what we need are kind of general strategies that tell us what to do for different categories of histories to make our lives a bit easier. The next complication, and we'll see this is going to get quite complicated at some point, has to do with how we evaluate the payoffs. Now, for a finitely repeated game, such as the Rubinstein bargaining game, which we saw before, we just add up the payoffs from each period, and quite often we use discounting. So in the bargaining game, discounting uses the fact that the longer you go on negotiating the more costly it is, such as negotiating a divorce. The longer the process goes on, the more you both have to pay lawyers. So it's eating into your funds. Or you're negotiating some sort of merger with another business, for example. The longer that you spend negotiating that, the bigger the waste of money is that you're spending on these negotiations that you could have spent on other investments. So discounting is quite common. We're also interested in infinitely repeated games, where we're particularly going to focus on a neat trick where we use the average discounted sum of the payoffs. So this is where things get a tiny bit complicated, but if we think about the utility to player I at time period t being equal to player I's payoff in time period t, and some discounting parameter delta being less than 1, which we also saw in the Rubenstein bargaining example, then the average discounted sum of the payoffs is equal to, well, we've got this ut being the payoff in time period t. That's going to be discounted back, and that's going to be equal to delta t to the minus 1, so delta to t minus 1. The reason for that is in the first period, there's no discounting. So when t is equal to 1, this term here needs to be 1. So we put t is equal to 1. 1 minus 1 is 0. Delta raised to 0 is equal to 1. In the second period, t is equal to 2, and then we need to multiply u in period 2 to player I by delta. So that's why we've got this delta t minus 1. So this is sort of the sum of the discounted payoffs. And then to get the average, we're going to multiply it by 1 minus delta. Now, where does this 1 minus delta come from? Well, you might recall from your math days, maybe not all of you have seen this, but some of you will have studied how to sum a geometric series. So for example, imagine that you had some number delta that's less than 1, which we have here, and you have the sum 1 plus delta squared plus, each time multiplying by delta. So the term delta here multiplied by delta gives delta squared. Add another delta, we get delta cubed, and so forth. And we can write it in the summation notation, but this is the cool thing: for delta less than 1, we end up with the sum equal to 1 over 1 minus delta. When we've got a finite sum of m terms, which means that it ends with the term delta to the m minus 1, or if we write it in terms of the summation notation here, instead of having infinity, we have m, then it looks slightly different. There are different tricks that you can do to work out what it's equal to, but basically it's equal to this. So it's equal to 1 minus delta to the raised to the power of m divided by 1 minus delta. And actually these two things are similar, because if we take m all the way to infinity, we have a number less than 1 raised to infinity. That's going to be equal to 0. So this whole term here is going to disappear, and we'll end up with the same thing. We'll see how we can apply this to get this average discounted sum of payoffs a little bit later in this lecture. Okay, so suppose we've got a finitely repeated prisoner's dilemma. That is, we know that it's going to be repeated for capital T periods. We're interested in working out what a subgame perfect equilibrium of this repeated game looks like, and we're going to try to solve for that, as we've seen before, using backward induction. Now, at any period capital T with some history, so we're on some branch of the tree, the game is going to end tomorrow. So once we reach that final point in period T, we've only got one more to play. And then we can forget about what's happened before. We've just got a one-shot prisoner's dilemma. And we know there is only one Nash equilibrium, which is defect. So basically we're taking that very last branch or leaf of the tree, which is its own subgame. So we know for a subgame perfect equilibrium, this equilibrium here must be part of it. So regardless of what's happened before, once we reach that final point, the players in a Nash equilibrium must play defect, defect. So what happens when we reach the period t-1? Well, we know in the last period, period t, that our player will play defect no matter what. Nothing we do in t-1 will influence what happens then. So we only really need to care about the payoffs now in t-1. What's happened before doesn't matter, and we know what's going to happen afterwards. So essentially, it's like playing a one-shot game again. And that means we know what will happen. There's only one equilibrium, that's DD again. So defect, defect. And we can follow that back to t-2 and so forth. At every point we know afterwards, players will play DD. Before isn't important. We're always going to get DD in each point. So players will be playing defect until the beginning of the game. That's not very exciting. It tells us there's only one subgame perfect equilibrium of a finitely repeated prisoner's dilemma, and that's defecting at every point in time. So when there's finite repetition, there's no cooperation. And this has actually got a special name in game theory. So in any finitely repeated game, we know there must be some last period. And because there is no last period, there's no future from that point. So we must play the Nash equilibrium in that point. But if the stage game being the one-shot prisoner's dilemma, so that 2x2 matrix, if that's only got one Nash equilibrium, that means there's no way to reward someone or punish players for things that they've done in the past, because we're just playing that Nash equilibrium at the final point, which means we're playing it in the second final stage and so forth. So repeating the stage game doesn't change the prediction of what the players will do. And this is sometimes known as the end game effect. Now that doesn't seem very satisfying for us. This idea that because the game has a finite number of periods, even if they are very, very long in the future, then that we must have this Nash equilibrium occurring in every stage game. Doesn't feel satisfying, particularly for these arguments about how humans have evolved to cooperate, to show empathy, and to show altruism, and so forth. So to think about this theoretically to match with what we see empirically in the real world, we consider an infinitely repeated game. But what we mean by that is not necessarily that players must play forever or live forever. A typical way of interpreting an infinitely repeated game is that it's going to end, but we don't know when it's going to end. And if you participate in some experiments that economists run at our university, at other universities, in different labs, this will often happen. You'll be told you will play the game for a certain number of periods. You don't know exactly how many periods, but it's between this and this. Or sometimes we'll say in every period there is a 5% chance that this is the last period, something like that. So we can suppose, for example, that at the end of each period, we go on to the next period with some probability, say delta, but that the game ends with some probability 1 minus delta. So then we can think about that delta as a discount factor when we do our calculations, even though what it means is the probability that the game actually ends. So the probability that we play the game in the first period is for sure 1. And then the probability that we play it in the second period is the probability that the game continues, which we know is delta. So it's 1 times delta. What about the probability that we get to period 3? Well, the probability that we play period 3 is equal to the probability that we play period 2 and that it doesn't end after period 2. So that's equal to delta times delta, which is delta squared. In other words, our discounted sum of payoffs, that familiar formula, is the expected payoff to a player at the beginning of the game. So what we're going to look at now is how to consider subgame perfect equilibria in an infinitely repeated game with either this this probability, this fixed probability that we don't continue every period, or equivalently that there's discounting of payoffs, which is sort of makes our life a bit easier to think about it that way. But we need to get a few things straight first. So what exactly is a subgame perfect equilibrium if there's an infinite game? Because that means that our game tree is infinitely large with no endpoint, no terminal nodes. So how can we do backward induction if there's nowhere to start from to go back from? Do we even know that every infinitely repeated game has a subgame perfect equilibrium? And how do we check whether some strategy profile is a subgame perfect equilibrium, especially considering that a strategy profile must give the actions for every possible history that can emerge? So this sounds quite complicated. But again, we'll see that there are some nice tricks that we can use to make our lives easier. The first thing to think about is that subgame perfect equilibrium is not defined by backward induction. It's just a technique that makes our life a lot easier to solve it when we have a game tree. But subgame perfect equilibrium has a different definition. Its definition is defined by a strategy profile that induces a Nash equilibrium in every subgame. So then we need to think about what a subgame is for an infinitely repeated game. And that is every possible history that can happen. Every possible history tells us every possible branch of the tree that we could be on, even though our tree doesn't have an end point. So those are all of the subgames, as long as a strategy profile is such that no player has a profitable deviation at any history, then we've defined a subgame perfect equilibrium. So now we know what it is, but how do we know that there's at least one in this infinitely repeated game? How do we know that it exists? And how do we know that every infinitely repeated game has one of these? Well, we know that it is the case because we know that playing a Nash equilibrium of the stage game at every history, at every moment, playing that Nash equilibrium would be a subgame perfect equilibrium by definition. Now there may be more than that, but at least that one would be a subgame perfect equilibrium. So we can be sure that it exists. But how can we check whether some strategy profile is a subgame perfect equilibrium? We know what a subgame perfect equilibrium is now in this infinitely repeated game. We know that it exists, there's at least one. But how can we check whether some strategy profile also fits the bill? Well, the problem is that normally we would check for deviations to see whether or not they're profitable. And if we say no deviation from this strategy profile is profitable, then we would say we have a subgame perfect Nash equilibrium. But we can't check infinitely many possible deviations. So for example, you could deviate at a particular history and follow the equilibrium strategy everywhere else. So you follow the equilibrium strategy all the way to some point T, change one time, maybe you're playing D, 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 change to C, come back to D and keep going. So that's a one-shot deviation. You've deviated from the strategy profile just one time in a one-shot game. But you can also do different sort of deviations. You could deviate every second period, every third period, every odd-numbered period, so forth. Or you can deviate depending on what your player has done the period before. So that's sort of going to be dependent on your partner's strategy, and we're going to see this will be a common form of deviation to look at. Fortunately for us, there is a nice theorem in game theory which makes our lives much easier at this point, and it's known as the one-shot deviation principle. What it says is that if we have an infinitely repeated game with discounting, then if there is a profitable deviation from the strategy profile, there will be a profitable one-shot deviation from that strategy profile. So we've got to test, in theory, we've got to test for all possible deviations, infinitely many ones, to see if there's a profitable one. But the theorem tells us if there's a profitable one, then there's a profitable one-shot deviation, which means if there's not a profitable one-shot deviation, then we don't have any profitable deviations across the infinite span of deviations, which means we've got a subgame perfect Nash equilibrium. So the one-shot deviation principle means we only have to check for one-shot deviations in order to establish whether a candidate strategy profile is indeed part of a subgame perfect Nash equilibrium. So what does that mean for our strategy going forward? What it means is that we need to ask ourselves, at any history, would a player wish to change their strategy, switch to another action of the stage game at this history, and then follow the equilibrium strategy everywhere else? So, for example, if we're considering playing D all the time as a potential strategy profile that may be subgame perfect in equilibrium, we can look at D, 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 T, D, 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 and ask ourselves, does it make sense, at point T, D, 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 C, D, 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 confuse myself. Does it make sense at this point T to deviate to C or not? Or would this player have been better just playing D the whole time? We're looking for that one-shot deviation. So now we've got all the tools we need to answer the original question, which is, can we sustain cooperation between two players in an infinitely repeated prisoner's dilemma? Well, the answer, the spoiler alert, is yes, but only if the discounting factor is high enough. So let's see what the general idea is of sustaining cooperation. Suppose we are to play CC to give us this maximum group payoff, 2-2. If I deviate to D, I screw you over today and I get an instant gain. I go from 2 to 3. But you might punish me and I might be punished later, maybe for multiple periods. If I care about that future punishment enough, then I won't deviate today. But if I don't care about what happens in the future, or at least not very much, I discount the future quite a lot, then it might be in my interest to grab that instant gain today, even if I get punished for many periods in the future. Now, there are many different subgame perfect strategy profiles that can sustain cooperation on the equilibrium path. But they differ in what happens off the equilibrium path. They differ in terms of what happens if a player deviates from playing CC in every period. So we're going to look at two very famous strategy profiles. The first called Grim Trigger and the second called Tit-for-tat. Both of these, in theory, can lead to both players cooperating forever, playing cooperate, or CC in every period forever. Where these two strategies differ is in what they specify for the punishment if a player deviates and goes to something else from CC. So let's start with the Grim Trigger. The Grim Trigger strategy says, we'll play C at the very start, we'll cooperate. And if you play C back, then I'll keep playing C. So I'll cooperate so long as you cooperate. We start, and if you play C, then I play C, and we sort of go in this loop of playing C together. As soon as someone defects, if you play D, that's it, my friend. I am playing D from now on forever. So as soon as someone plays D, we are stuck in this loop forever of defecting. So for example, you've got a partner where if one partner cheats on the other, I was going to say one player cheats on the other player, I guess it's also kind of appropriate. As soon as someone cheats, that's it. Game over. We're never going to cooperate again. But as long as we stay faithful to each other, we'll keep staying faithful to each other. So how do the action profiles transition into each other? And this will help to give us an idea of the different sort of histories that we can get. I'll try to move out of this text a little bit here. So if we start at CC and keep playing CC, we're going to, if both players are following the Grim Trigger strategy, then the transition profile doesn't deviate. I'm playing C if you play C, you play C if I play C, we stay there forever. Likewise, if before we had DD in the last period, both of us have the Grim Trigger strategy, which says if someone plays D, then play D, we again will move back to DD. If somehow we find ourselves at, say, CD or at DC, then our strategies tell us play D the next period, play D the next period. So what that means then is we will always go to DD from either of these mixed sort of areas. The reason is that if someone has defected, then I'm going to defect forevermore. Even if you change back to C for some reason, it doesn't matter. You screw me over once, that's it. So for that reason, CD and DC both in the next period move us to DD. And we need to know this transition path because we want to write down the conditions under which a pair of Grim Trigger strategies, one for me, one for you, we play against each other, can be a subgame perfect equilibrium. So because of this one-shot deviation principle, we just need to consider the situations in which a player might deviate from that, and we need to work out under what conditions is that deviation not profitable. That's what we need to look for. Now, of course, this tree is massive. There are infinite different possibilities that could have occurred, but because of what we saw in the previous period, we can narrow down that infinite range of histories to certain categories of histories because of the transition paths. So these are histories or things that have happened over the past that mean that at this period we play CC, or that category of things that could have happened in the past that tell us that DD will be played at this period. So we're basically categorizing all the histories that can happen, the different things that could have been played at each time period. We're putting them into two boxes. The box that says at this time period play CC, and the box that says at this time period play DD, because those are the two possible outcomes that can come from the transition period. So this has an arrow going into itself, CC. DD has arrows coming into it from three different points, DD, CD, and DC. So those are the boxes that we sort of categorize. Now, at any history where DD is to be played, which means in the last period there was either DD or CD or DC, then we know that DD will be played now and forever for the future. We're in a loop. But we know also that DD is the stage game Nash equilibrium. So there cannot be any profitable one-shot deviation when DD is to be played. So that's the easy case. What about when CC is supposed to be played? Well, if I continue to follow the Grim Trigger strategy and I've seen CC, then that means still playing CC. So if we keep following the strategy, we don't try to deviate, then we get C forever. We want to know what is the deviation and could it be profitable? So the deviation is, of course, to play D in this period. And remember, we only need to consider a one-shot deviation. So we play D in this period, and we'll keep playing the Grim Trigger strategy from then on. Basically, if you think about time period 1, 2, 3, 4, up to T, we say play Grim Trigger, play Grim Trigger, play Grim Trigger, play Grim Trigger, deviate, play Grim Trigger, play Grim Trigger. So we're only deviating for one period. The question is, can this be profitable? Well, we know that if we play D in this period, our partner is going to play D from then on, which means we're going to play D from then on. We're going to end up with DD after that. So the outcome in this period is going to be DC. When we deviate, we screw over our partner. But from then on, it's going to be DD for both of us. So we now want to work out whether this one-shot deviation can be profitable or not, and under what conditions. Now, because players can earn different payoffs in different rounds, it's more convenient for us to try to normalize the profits by thinking in terms of the average discounted sum of the payoffs. So if the total payoffs, pi, are equal to the sum of the discounted payoffs in each period, then what we really want to work out is the average per round payoff. What was the hypothetical amount we could have been given every period, a constant amount, that would equal this total amount equal to the sum of the discounted payoffs in each period if it was earned in each round. And we'll see that it's equal to this strange sum here. Now, how do we get this strange number, particularly this 1 minus delta out the front? Well, we know that the total payoffs that we'll get, the total discounted sum of payoffs, is equal to the payoffs we get in every time period T, discounted by the appropriate amount, and we add all of those guys up. So that gives us our total payoffs pi. We want to find what is this constant pi bar. What's this constant amount that we could have put in for this changing amount in every period? What is this average per round payoff that would have given us this same total? And how do we find that? Well, we know from what we saw before with the sum of a geometric series that the sum of just the deltas is equal to 1 over 1 minus delta for an infinite sum. So we know this already. Now, if we multiply the left side by a constant, this pi bar, if we multiply it by pi bar on the left, it's like multiplying it by pi bar on the right. So multiply it by pi bar on the left, you multiply it by pi bar on the right. But now we've got here the same thing that we had up here. So we know that this is equal to pi. Most importantly, we know that pi bar over 1 minus delta is equal to pi. We want to find what this pi bar is equal to. We rearrange that. When we rearrange that, we'll see that it's equal to pi times 1 minus delta. So we'll see this on the next slide. Pi times 1 minus delta is equal to pi bar. And then the last step in this mathematical trickery, sorry, I'm in the way again, aren't I? Here we go. The last thing we have to do for this mathematical trickery is to replace that pi by what we know that pi is equal to. And that pi is equal to, remember, this part here, this sum of the discounted payoffs in each period. So we do that replacement and we can work out what pi bar is equal to. So you can think about it as what's the amount that you would have been paid every period, exactly the same, that gives you this total discounted sum of payoffs. It sounds a bit confusing, but now at least we can see where this 1 minus delta is coming from out the front. And that normalization makes our lives a bit easier when comparing between two different sets of payoffs, trying to work out which one's bigger than the other one. So if the player follows her Grim Trigger strategy and she doesn't deviate, then she keeps playing C, keeps playing C, keeps playing C, the partner keeps playing C. Her average discounted payoff is going to be what she gets in every period, which is 2, discounted back for the time period, so delta t minus 1, and then summed up, and then multiplied. If we want to work out the average discounted payoff, remember we need to multiply it by this 1 minus delta. And when we do this, remember that this part here times 2 is equal to 1 over 1 minus delta times 2. So what we end up is this 1 minus delta is over here, times 1 over 1 minus delta, that's this part here, multiplied by the 2. So of course, these things cancel out and we end up with just 2. And that makes sense because what we were trying to find is what's the amount that you would be paid every period to equal your total discounted sum of pay-ins. But you're getting 2 every period anyway. So it's going to be 2 every period. It's just the same. It's like taking an average. What's the average of 2 in this period, 2 in the next period, 2 in the next period? Well, it's 2. So we've got our 2. What about if we deviate? Well, if we deviate, we're going to get D in this period, and then we're going to be punished from then on, getting DD after that. So what's the payoff going to be? Well, 3 is what we get from the initial deviation, and after that we're going to get 0. So we get 3 first, then we get 0 for every period after that, discounted back. So it's 3 plus delta times everything after that. This extra delta is because we're starting this sum 1 period afterwards. So we add this delta in to discount that. And then we want to find the average discounted payoff. So we've got to multiply it again by this 1 minus delta. That's just so that we can compare this 2 to whatever comes out over here. And what is it equal to? Well, it turns out it's equal to 1 minus delta times 3. So now we're basically comparing the 2, which is what you get if you keep following the strategy, versus the 1 minus delta times 3, which is what you get if you deviate from the strategy. Now, if we're going to find this strategy to be a subgame perfect Nash equilibrium strategy profile, then it must be that the equilibrium payoff has to be at least as good as the deviation payoff. In other words, there cannot be a profitable one-shot deviation. So for us to have a subgame perfect equilibrium strategy profile, it must be that 2 is greater or equal to 1 minus delta times 3. And after all that work, we now see that it all depends on delta. If delta is high enough, as in if delta is at least 1/3, then there's no point in deviating, which means the Grim Trigger strategy for both sides is a subgame perfect Nash equilibrium. And what does this mean, this delta being greater or equal to 1/3? What's the logic behind it? It means if we care enough about the future, the higher the delta, the more we care about the future. So if we care enough about the future, we care about being punished, we won't deviate from our Grim Trigger strategy. But if we don't care enough about the future, or the probability of the game continuing is too low, which remember is the other interpretation of this delta, then the temptation to grab those instant payoffs now is too strong, and the Grim Trigger equilibrium breaks down. A quick side note about some applications which researchers have applied this to. Tourist traps. If you go to Venice, you go to Paris, you go to Prague, you'll often go to these places where you want to buy some gifts and they offer you fantastic deals, and they have, of course, full information about how much the artifact is worth, or the handbag, or the sculpture, or whatever. You don't know. So they've got an incentive to screw you over in this period, and you've got an incentive to trust them so that you can get the product, and you'll punish them in the future if they are screwing you over. But of course, why do we call these tourist traps? We call them tourist traps because the tourists often do get screwed over. Why do they get screwed over? Because it's usually not a long-term relationship. When the tourists are in town, as opposed to the locals, there's not much chance for the tourist to punish in the future, because you're not going to have this interaction many times. In other words, the delta is very low. The probability that this is the last time that you interact with each other is quite high. The probability that the game ends is quite high. So because that delta is quite low, it's hard to keep that cooperation going. It's also been applied in a relationship sense, particularly in lieu of particularly related to the empirical result that men in the military on service tend to be less faithful to their partners than men who are stationed at home or not in the military. Now, I'm not for a moment claiming that game theory can explain this. It's obviously a large field in sociology and psychology with other theories that can try to answer this. But if one wanted to relate it to this repeated game type analysis, and it has been done by some researchers, the idea is that if you're in a high risk sort of situation, you've got that you're in a conflict zone, or if you think in terms of spies, someone like James Bond, where the probability that things end quickly is quite high, then the temptation, the payoff from instantaneous gain from being unfaithful and basically choosing D with respect to your partner becomes higher, essentially. Okay, so that's the Grim Trigger strategy. What's the tit-for-tat strategy? You might have heard this phrase before, tit-for-tat. Well, this strategy is slightly more involved, and it goes like this. We'll start with C again, but in every period, I'll just play whatever you played in the last period. So I'll play C at the start, and if you play C, then I'll play C, and then you play C, then I'll play C. If you play D in this period, then next period, I'll play D. So if you play D, the other plays D, then I'll play D in the next period. Now, once I'm on D, it again depends on what you do. If you play D, then I'll play D in the next period. If you play C, then I'll play C in the next period. What does that mean for our transitions between the action profiles? Well, it's a bit strange now, because if both players are playing CC, then we're always going to end up back at CC. Both players follow the tit for tat, and the other one plays C, they'll keep playing C. And the same for DD. But if we've got a mix in any period, a CD or a DC, then we end up in this loop where we're both swapping every period. So say it's I play C, you play D. That means we both need to swap in the next period. So now I play D and you play C, and we end up in this loop happening between these two sort of asymmetric strategies. So what's the value of this loop here, this alternating between CD and DC? What's the value of this one? Because this one's going to be tricky. Suppose we start with me playing C and you play D, and we alternate forever. Next period I play D, you play C, and so forth. What we want to know is how to calculate player one's average present value for such a continuation, or the average discounted sum of payoffs for this sort of loop that we have. Well, first we'll work out the total discounted sum of payoffs, which is, well, that's going to be equal to the discounted sum of payoffs from playing CD, and that's going to occur in round 1, not round 2, because then it's DC, but then we switch back to CD, so round 3, not round 4, but round 5, not round 6, but round 7, so the odd rounds. So we need the discounted payoffs from CD in the odd rounds, and we need the discounted payoffs from DC in round 2, round 4, round 6, and so forth, which is the even rounds. So what we're adding up is something a bit strange. If I play C and you play D in the first period, then I get -1. The next period, I'm going to play D and you're going to play C. So that means that I'm going to get 3. After that, I'm back to -1 again. Then I get 3 and so forth. And each time we're discounting it. So there's a delta next to the 3. There's a delta cubed next to the 3. There's a delta squared next to the -1. Over here, we'll have a delta to the power of 4 times -1. So we've kind of got these 2 different sums happening together. And each of these sums has got deltas where we're sort of going up +2, +2, +2 every time, which makes it a tiny bit complicated to write out. So what we just saw before, this sum, can be written out as 2 separate sums. We see here 2 separate sums. And we can, if you put in the different values for k is equal to 1, k is equal to 2, k is equal to 3 here, and you do the same for this side, you'll see that it equals to this sum over here. That's probably the easiest way to understand this. But think about it. Put k is equal to 1 in over here. You get 2 minus 1 minus 1 is 0. Delta to the power of 0, that's just equal to 1. So the first term is -1. That's when k is equal to 1 over here. When k is equal to 1 over here, we get 2 times 1 minus 1 minus 1. That's equal again to delta to the 0, which is 1, times 3 times delta. So we end up with delta times 3. What about when k is equal to 2 over here? Well, then we get 2 times 2 is 4, minus 1 minus 1. So that's delta to the 2, delta squared, times -1. So the next term is delta squared times -1. And you can keep putting in the k's to see that it actually adds up to this sum. Now this sum looks a bit confusing, but we can use the same techniques we saw before with the geometric series, and you can work these out for yourself, to find that the sum of the infinitely repeated, so the sum of this geometric series here is equal to 1 over 1 minus delta squared times this -1. And on this side over here, it's equal to 1 over 1 minus delta squared times this delta out the front and times the 3. Put all this together and we finally end up with this term here, which is the total discounted sum of payoffs for player 1 when alternating between CD and DC, starting at CD. Now to work out the average discounted sum of payoffs, we use the same trick as before. We multiply by 1 minus delta. So, this is a quick mathematical note if you wanted to see how we got from the top line here to the next line down here. I won't go through it in the video, but you can go through the math yourself if you'd like. So, like I said, we take the total sum of payoffs, we multiply it by 1 minus delta to get the average discounted sum of payoffs, or the average present value. Now this 1 minus delta squared here, we can rewrite 1 minus delta squared as 1 minus delta 1 plus delta. I think I can try my best to write this with the mouse. 1 minus delta. It's quite difficult to do this, it turns out. But anyway, I hope you understand that. So 1 minus delta 1 plus delta is equal to this 1 minus delta squared. So we can replace that down the bottom and you'll see that this 1 minus delta and this 1 minus delta will cancel out, which is why we end up with 1 plus delta at the end, at the bottom. So that gives us over here our final amount for the average discounted sum of payoffs for player 1. Now remember that player 1 and player 2, they started at a different point. So player 2 started with getting D on the first go. Player 1 started with C. So there's a slight difference in the payoffs. We can calculate those for player 2 exactly the same way as before. We can again use the same trick to cancel out this 1 minus delta from the top and the bottom, and we end up with a slightly different answer here for player 2's average payoffs. Okay, that was a lot of work, but we needed to do that. That's actually the hard part. Now we check for subgame perfection by looking at profitable deviations, and we'll see that this part is mathematically much easier. Now, if you remember the transition profiles that we looked at before, again, we're going to take the infinitely many histories and we're going to put them in different boxes, different categories. Before, in the Grim Trigger, we had 2 possible categories of histories, the ones that lead to CC and the ones that lead to DD. But now it's a bit different. Now there are 4 different possible histories. So it depends about whether or not the current period's play is supposed to be CC, according to the tit-for-tat strategy of both players, is supposed to be CD, is supposed to be DC, or is supposed to be DD. So there are 4 possible profiles. All 4 possibilities could happen depending on what happened the period before from tit-for-tat strategy. So let's say that the current period of play is supposed to be cooperate. And what's the payoff if we continue to follow the same tit-for-tat strategy? Well, if we follow the equilibrium strategy, we just keep getting CC forever. If you remember from our transition profile, when both players play tit-for-tat and we're at CC, the arrow comes back to itself. We play CC forever. What's the payoff from deviating? Well, the payoff from deviating is getting into that loop that we saw before. DC, CD, DC, CD, and so forth. And we get to that loop starting with DC, because if we deviate, we get this D in the first period and then we start the loop. What about if the history tells us that we're at DC this period? For example, if the last period was CD, in this period, DC is what we should end up at. Well, if we follow the equilibrium, we're in this loop forever now. DC, CD, DC, CD, and so forth. If we deviate in this period, and remember we're only looking at one-shot deviations. So deviate in this period, go back to tit-for-tat from then on. If we deviate in this period, instead of DC, we get CC, and that puts us back in the CC loop forever. And we can do the same for if the history tells us that we should be at CD today and we follow the equilibrium, we're in the infinite loop, CD, DC, and so forth. If we deviate, we change from C to D, and then we're stuck in that DD loop forever. And of course, if we're in DD, the equilibrium is to stay in the DD forever. The deviation is to switch to C, and then we get into that loop of CD, DC, CD, DC, and so forth. Now, here's the trick. Game theory, you've learnt by now, particularly in repeated games, has a lot of tricks. So here's the trick. We need to check whether or not a tit-for-tat strategy from both players can be a subgame perfect equilibrium. We need to make sure there are no deviations, no profitable deviations. Look at the first case, CC. Without doing any of the math, a deviation is profitable if the infinitely alternating sequence starting with DC today is better than CC forever. If the loop starting with DC today is better than CC forever, there's a profitable deviation. But now look at the history that leads us to DC. If CC forever is better than the loop starting with DC today, there's a profitable deviation. So what does that mean? Well, if we've got subgame perfect, a subgame perfect equilibrium, then can be no profitable one-shot deviation from any history. But here we've got exactly the reverse of each other. In the CC case, which is the top history, we need that the DC loop is not bigger than CC forever. But in the DC case, we need that the DC loop is at least as big as CC forever. It's like saying we need that delta is at least as big as a third, but we also need that delta is not bigger than a third. We need both of these things to be true in order to have a subgame perfect equilibrium. So we need the opposite conditions of each other. It becomes very, very fine. We need a very precise number in order for these opposite things to be exactly holding at the same time. And if you look at CD and DD, if you look at this pair down here, you actually find the same. So in the CD history, the past play that leads us to CD being the supposed next period play, for there to be no profitable one-shot deviation, the CD loop must be at least as big as DD forever. But in the DD history, sorry, move out of the, here we go, move out of the way. In the DD history, the CD loop cannot be bigger than DD forever. So again, we have exactly the opposite conditions, and they need to hold at the same time. So what we say is that because we don't have a range of values anymore, we need these two things to be exactly balanced. We actually call this the knife edge case, as if you're balancing on a knife's edge. So the pair, for example, as we saw before, of CC and DC cases have exactly the reverse conditions for each other. And so the only way that they can hold is if player one is indifferent between the equilibrium and deviating in both cases. Player one must get exactly the same payoffs from the deviation and the equilibrium play. And it's the same for the pair CD versus DD. In this case, again, the conditions are the reverse of each other. Beta cannot be greater than this, cannot be less than this. So again, it must be that player one is indifferent between the payoffs they get from equilibrium play and deviation. Is it possible to get such a fine condition? Well, let's see what we would need for this to be the case. What's the value of getting CC forever as an average discounted sum of payoffs? Well, we've seen this before, it's just 2. You get 2 every period. What's the value of the infinite loop that starts with DC and then goes CD, DC, and so forth? Well, it's the payoff. We saw this in the previous case when we analyzed it. It's exactly this payoff 3 minus delta over 1 plus delta. So we require that these things are equal to each other in order for both of these conditions to be satisfied at the same time. And that means, again, we can solve this for delta and find that now we don't have a range anymore, because one of the conditions says delta must be at least a third, the other condition says delta must be no more than a third. And it turns out the only way we can satisfy both is if delta is equal to a third. So that gives us only one value that can hold, and we haven't even checked the other 2 histories yet. So let's check those. What's the value of getting DD forever? Well, that's just 0 in every period, that's just 0. What's the value of the infinitely alternating loop starting with CD and then going to DC? Well, it's similar to the other payoff, just slightly different. 3 delta minus 1 over 1 plus delta. We set those equal, and what do we find? Delta's equal to a third. Exactly the same as the earlier condition. So this tells us that if delta is equal to exactly a third, then 2 players who both adopt a tit-for-tat strategy can continue to play that forever as a subgame perfect equilibrium. But this is a very finely balanced equilibrium. That means if any player deviates slightly, if there's any small change in delta, such as 0.31 or 0.29, or 0.332, then we wouldn't get the result. We would not be able to sustain cooperation in a tit-for-tat subgame perfect equilibrium. And we only get it in this case because I chose these numbers to show the one example that gives us tit-for-tat working. So from a theoretical point of view, unless the numbers are just right, it's not possible to get this tit-for-tat strategy working out to be a subgame perfect equilibrium. But here is where experiments and theory are good tests and complements of each other, because it actually turns out that tit-for-tat, rather than grim trigger, is quite a good strategy in practice. And there have been further advances in game theory to try to explain why this is theoretically. But this was actually tested back in 1980 in a computer experiment in the 80s. So a famous game theorist, Robert Axelrod, he launched a competition where he asked people to write computer programs giving their characters essentially rules, basically equilibrium strategies, just like that poster on the wall that we spoke about. So play grim trigger strategy, which means if your partner plays C, then you play C. If they play D, then play D forever. That's all you have to tell your computer program. Or tit-for-tat, if your partner plays C, play C next period. If your partner plays D, play D next period. And that's it, essentially. And people needed to write in their programs, their strategies, send them in, and then they knew that they would play the Prisoner's Dilemma for 200 rounds against another program, and then they would play against the next program and the next program, each time for 200 rounds. And at the end, we wanted to see which rules, so which program with which set of rules would have the highest payoffs overall. Kind of like you take a game of evolution amongst different types of species and you cram it all into a short period of time to see which ones survive at the end. So he invited some specialists for the first tournament. The second tournament, he opened it up to everyone. There were some very complicated programs, but in the end, the winner had a very, very simple program. Rather than the many, many lines of code that were in the other programs, the winning program had only, I think, 10 lines of code. And it was the tit-for-tat strategy. So exactly what we saw before, which theoretically should not be able to sustain cooperation unless there are very specific levels of delta. But what we find is that actually the tit-for-tat strategy does well against a range of different programs. So against very mean grim trigger programs, it does quite well. Against naive programs, it does quite well. It basically hedges its bets, and it does quite well against a range of different programs. So the computer programs are not necessarily doing the best response to each other. They're just following their own strategy no matter what, and sometimes it's going to be the best strategy, but against other opponents, maybe not. But Axelrod concluded that the tit-for-tat strategy sort of had the best across a range of different opponents that it could meet. It was nice against nice opponents and forgiving against opponents that screwed it over, such that it didn't punish forever, but allowed some way for both sides to keep earning payoffs in the long run. And there's a very interesting, quite recent podcast that Radiolab put out. Radiolab makes fantastic podcasts, and this was from September last year, September 19. You can download it. You can click on the link here or go to Radiolab's website and search for Tit-for-Tat. And it's quite a fun read, not very long, quite interesting. To talk about Prisoner's Dilemma as well, which you should know far more about now than even those radio producers. There are some further academic articles that you could also read about this if you want further information by Robert Axelrod himself. So we've covered repeated games today repeated prisoner's dilemma in both a finite and an infinite context. As is now becoming a bit of a custom, I want to leave you with some sort of brain teaser for home to think about in a way of applying the skills that we've looked at in hopefully a fun sort of context. So you might know the game Tic-Tac-Toe, also called Noughts and Crosses. I've put also the Mandarin name for this game. Just do you put an X, do you put a 0 in a 3x3 grid? And you're going to move first. Now you probably know, having played this on the dirt when you were a kid, that the game should be a draw. It should be a draw, and Bob knows it's a draw, so Bob doesn't even bother. He's so confident that it's going to be a draw that he's written down a guaranteed non-losing strategy on a piece of paper, just like he was writing it for a program and sending it into one of Robert Axelrod's competitions. And this is what his strategy says. If it's my turn, Bob's turn, and Bob can win, play the winning move. Else, if you know computer programming, it's sort of an if-else type sort of function here. If I can't play a winning move, but you can play a winning move, then I stop it. If I can't play a winning move and you don't have a winning move that I should stop, then play in the center, the very middle one if it's possible. If that's not possible, then play in a corner. And if all of those things aren't true, I can't play a winning move, you can't play a winning move, I can't play in the center, and I can't play in the corner, then I just choose randomly. That's my strategy. Now, if you read this strategy, it sounds pretty logical actually. This sounds like a very good strategy to play in Noughts and Crosses or Tic-Tac-Toe. See if you can show how you can take advantage of this strategy and guarantee that you will win if you move first. So I'll leave this with you. We'll discuss it in the next lecture. I hope you enjoyed this, and I will see you next time.